All right, so this is for section 12.2, and it comes from when we're preparing to do logarithmic functions, because understanding the inverses of exponential functions is the definition of logarithmic functions. But we're just bringing it out for this one section. Let me click on here. 12.2 talks about inverse functions, and we already did 8.2, which is the definition of function. Once you know the definition of function, which is that for every x value there's exactly one y value. So each element in the domain has a unique element in the range. Remember how we talked about that? Mm-hmm. Okay, good. This is then one step further in terms of being like kind of whittling down this specific characteristic. See, we started out, actually I'll grab the pen, with just a relation. A relation is just a set of ordered things, ordered pairs. And then a function itself is a relation that has the characteristic that every x value goes to exactly one y value, or in general, every domain value goes to one unique range value. So a one-to-one function, this is the new part, is one-to-one if it's first of all a function, which means that every x value goes to exactly one y value. But then at the same time, every y value comes from exactly one x value. And you'll make more sense of it when we actually do a map of it. So you don't have to necessarily write this whole thing down. But that's a one-to-one function. Often you'll see people just go one-to-one function and abbreviate it. Okay. So determine whether each function, and they're already telling us that they are functions, describes a one-to-one function. But let's double check that they're a function. To see if they're a function, you could double check and see if there is ever a repeated x value, right? And there isn't. So that just further verifies that they are functions. But then, if it's one-to-one, you shouldn't see a repeated y value either. And see how they're all unique? So if you looked at the map on this, you'd have 1, 3, 5, and 6. 2, 4, 6, and 7. And 1 maps to 2, 3 maps to 4, 5 maps to 6, 6 maps to 7, and they're all 1-to-1. Every x corresponds with one y value and vice versa. And that's what it means to be one-to-one. So yes, this one is a one-to-one function. So it is a function because there isn't a repeat in the x's, but as soon as you see a repeat in the y's right here, you know that you're going to have something like this, and I'll go ahead and show it. Zero is going to 3, 3 is going to 7, 6 is going to 7, and when we talked about section 8.2, we talked about how you couldn't have more than one tail coming out. That's the definition of a function. The definition for a one-to-one function is that you cannot have more than one head going in, or it fails. See, on all of these, you see there's one tail coming out, one tail coming out, one tail coming out. That makes it a function. But it also only has one head going in, one head going in, one head going in. That's one-to-one. Over here, though, we've got every tail has only one tail. Every domain value only has one tail coming out. But you've got these two that have a 7. So they've got 2 heads going into the range. Remember how we had the vertical line test? That was to test for a function. So similarly, and the reason why that worked is you could run any arbitrary vertical line across the coordinate system, and if your graph got hit more than once, it failed to be a function. Or in other words, if it only hit once, it passed the test because it was indicating that each x value only had one output, one y value. Well, so what we have for the one-to-one test is, first of all, is it a function? If it is, then run a horizontal line test to see if it's a one-to-one function. So is it a function? Run the vertical line test. Is it one-to-one? Well, you'll find that out if you run a horizontal line test. What do you think? Is this one, first of all, is it a function? Right, so if I took any vertical line, it only would pass through the graph at any point once, right? So on this first line, it doesn't pass through at all. On this next one, only once, only once, only once, only once. And you have to say, well, it's not just going to work for these 7 lines or whatever. It's got to, or 6 lines. It's got to work for every single arbitrary line. So it's a theoretical thing. So it is a function for sure. Is it one-to-one? Well, imagine that you pass a horizontal line, and Jessica, you were right. No, it won't be a one-to-one function, because if you pass a horizontal line, it fails miserably many, many times. The only place where it doesn't go through is at the, yeah, it's what you call the vertex, at the bottom. So this line right here is the only one that would have a single touching point. Everywhere else, you're having more than one, so it is not one-to-one. That's funny. He looks like a face that's got his eyes punched out or something. Or crosses on the eyes. Let me actually remove this distraction. We're focusing on this right here. Okay, is this one a one-to-one function? My first question always, is it even a function? Yes or no? Yes, it is a function. That's the first part, just because any vertical line that you pass through will only pass through at one point. That's the VLT, vertical line test. So yes, it is a function. Then you have to ask yourself, is it one-to-one? Any line you pass through this way also will only pass through once. So yes. Note that we previously discovered the horizontal line represents a function, and it is not, but it is not a one-to-one function. So I'll show you what they mean by that. Remember when we were, Remember when we were talking about function or graphs that were not functions? One of your homework questions looked like this in section 8.2. Do you remember that? Okay. And we asked, is that a function? Is it?
No.
So that's not even a function. And then we talked about things like this. Are these a function? It's supposed to be horizontal, but is that a function? It's a function, but not one-to-one. That's the only point they're making there. And it's obvious that it won't pass the horizontal line test at that point. Everywhere else it passes. If there is a one-to-one function, then it has an inverse. We haven't even explained what an inverse is. We will in just a second. You can find it by just switching the coordinates. Once you've found it, you can relabel it with this inverse notation. And so that's pretty much all you need to know. We're going to do it in a second, but an inverse function is the inverse of the ordered pairs, which is found by just switching them all. Not reciprocating, switching.
So like your x and your y?
Right. So what was an xy point now becomes a yx point. You first need to have a one-to-one function, so if it is one-to-one, call it f. and has all those ordered pairs, then switch those ordered pairs, and now you've got an inverse function called f inverse. So let's see an example. First of all, is this a one-to-one function? It is a function. No repeated x values, no repeated y values. You could actually graph it out. We don't need to. Okay, if it is one-to-one, then we can switch this with that. You know, switch and switch. Switch this, and obviously I mean switch. For every single point that there is. And that new thing would be called the inverse. So this, since it's currently called the g function, we would call the inverse g to the negative 1 power, g inverse. Let me show you. So g inverse is going to be the set of these 4 points, 4, 3, 2, 6, negative 3, 2, negative 5, 4. I really like pictures, so I kind of can't help this. Let me see if this works out okay. 1, 2, 3, 1, 2, 3, 4, 5, 6, 1, 2, 2, negative 3, 4, negative 5. So that's the original function. And then the inverse. Yeah, it's weird what happens to it. So it actually reflects it across a diagonal. So if I was to show you, you can imagine like a diagonal fold right here. If you were to fold this up that way, and obviously this right here would leave an impression, fold them across one another and you'll get this new result. It's the same thing that occurs when you just switch them. So now you're going to get 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 5, 6, 1, 2, 6, negative 1, 2, 3, up 2. See where this one went right here?
Mm-hmm.
Went up here. And then negative 5, 4. Kind of weird, huh? The reason why it reflects across this line is this is the line y equals x, where 1 would be with 1, and 2 would be with 2, and negative 3 would be with negative 3. So anyway. Questions?
What I was thinking was 1 to 1 is when they're one number, 3, 4, 2, 3, but that 2 and 6 is not. One number off. Is that because it is?
Well, let me understand your first part.
Okay.
1 to 1 is that 3 goes to 4, 6 goes to 2,
Yeah, but
2 goes to negative 3, 4 goes to negative 5, and that they only came from 1 point. So 4 only comes from negative 3. There's no repeated 4 as a y value coming from a different x. 2 only comes from 6. So there's no y value of 6 that comes from anything other than 6. No y value of 2 that comes from anything other than 6. And negative 3 comes from 2. So that it's 1 to 1, it goes both ways. So now ask what you're asking?
no, that's excellent.
Makes sense? Okay. All right, here's the process then when you're given a rule and you want to find the inverse without having to graph it all out. Like I just graphed those 4 points and then I had to graph the other 4 points and interchange them and all that stuff. What you do is, instead of using y notation, use f of x notation. We learned this in section 8.2. That was one of the big objectives of that section. Then switch both of these, switching them in the rule will switch them everywhere. So you just interchange the x and the y. Then solve what you have there. So put it back into a solution of y and replace that solution that you have equal to y with the new notation for its inverse. 4-step process. You'll see what I mean by this in a second, but this is unlike the ones we've already been looking at where there are 4 points that you can actually just plot, because those are finite functions. We're talking right now about functions that are defined by a set of ordered pairs from a rule, not from a finite list. That's when you use this set of instructions, these steps. So let's try it. All right, so the original one right here was this graph, f of x equals 6x minus 1. And I'll graph that actually to the best of my ability. And my graph is going to look something like this. It starts at the intercept of -1, and then it has a slope of 6, which essentially means that the directions are go up 6 to the right one or go down 6 to the left one. Chapter 3 coming back to us. So I'm going to go up 6, 1, 2, 3, 4, 5, 6 over 1. Up 6, 1, 2, 3, 4, 5, 6 over 1. Very steep. Down 6, 1, 2, 3, 4, 5, 6 over 1. If we've done our graph well, they should all pass through those points. Has nothing to do with the steps we were just looking at, so let's get to the steps. The steps are rewrite the notation with y notation. Rewrite the function with y notation. Then switch x and y. By switching them in the rule, what you've technically done is you switched every single ordered pair that could ever be graphed from the definition of the rule. Does that make sense? Because now what was an x is now a y. What was a y is now an x. They've switched. So then this then can be solved for y. Solve it for y. They're already showing the work. You know, so let's see what they did. They subtracted. This is weird. Okay. They actually added the 1 over and then reflected the equation. See that? Kind of weird. You want to see the work on it? They took this and they added 1 to this side. Oh, excuse me, they had already interchanged these. Okay, they added 1 to both sides and then they reflected the equation. So they had x plus 1 equals 6y, but they wrote 6y equals, yeah, reflected the, right along the equal sign. Then they divided everything by 6 so they could have the y solved. And after you solve for y, then you just change the notation. And the reason why they do that is because it makes sense. If this is a rule where y equals something with x in it, and this is a rule where y equals something with x in it, how are you going to keep in mind which one was the original, which one was the inverse? Well, you use this inverse notation. Now, I actually want to graph this, but I don't want to graph it in the form that it's in because it looks weird. We would typically have written this as 1/6 x plus 1 back in the day, chapter 3. So I'm going to graph f inverse of x in this form, where here is your starting point, positive 1, and here is your slope. So your slope says go up 1 over 1, 2, 3, 4, 5, 6. This is where it kind of bites me to have not had the scale the same. Or I could go down 1 over 1, 2, 3, 4, 5, 6. And now I connect those. And my scale wasn't perfect, but you'll see, similar to what we saw in the one with just dots, if I was to make this diagonal, they would fold across each other. So what was here would fold down here, what was here would fold up there, and leave an impression on the other side that looks like this new thing. That new thing is the inverse. Thoroughly lost? Make sense, you guys? What's most important is that the step-by-step process makes sense. That you could go, yeah, that's the part that matters for our intents, for our purposes. Okay, so here's what we just already said, but with a to-scale graph. And this is the line y equals x. So what we're saying is, if you were to look at the graph, it would be symmetric across that line. So you could fold that as your diagonal, and they'd be the same images on both sides. You've got both graphs. You've got the original graph, and then you've got its inverse, found through the 4 steps. That right there is enough for us in this section. We could stop. I can't remember if I had some other things left here. Nope, that was it. Perfect.
Do you ever have to solve? Like once you do the inverse, is there a way you have to solve for like one that's like against the x then?
Well, once you have this, you want it to be a rule with x in it. And yeah, you solve for x every time you plug something in.
Okay.
Yeah, so like suppose I wanted to find out where is the graph going to be right here. Well, that is 1, 2, 3, 4. So if I want to find out where it's going to be at 4, I put f inverse of 4 in, and I do like I did in 8.2's homework.
Oh, and then do
I plug 4 in for x. You know, 4 plus 1 is 5, 5, 6. That would be the output. So I'm looking for the ordered pair 4, comma, 5, 6. And that's exactly where it's going to land, right before you get to the 1. Close to 6, 6.
And how would you switch them if it was the x plus 1 over 6? And how would you find the inverse to that one?
X plus 1 over 6?
It's in our homework, it's not asking it, because it's x plus 2 over 7.
Well, let's just do a homework problem. Let me pause this. Okay, so this is 12.2.1. So question 1 from homework 12.2. Give it to me.
It's the f equals x plus 2 over 7.
2 sevenths like this, or all over 7?
All over 7.
Okay. All right, and then the directions are find the inverse.
And find the inverse of the 1.
By the way, they have told you that it is, first of all, function, and it has to be because it's written in function notation. It's some sort of like output y with this as our rule. But the reason why we know it's 1-to-1 is because if we would have looked at the graph, it would have passed the vertical line test and the horizontal line test. In other words, there's only one output for every input and one input for every output. It would have been 1-to-1, but they already told you that. So then I'm just kind of summarizing, find the inverse. Well, there's the first part of finding the inverse right here. Use the y notation. So first step, rewrite it as y equals x plus 2 over 7. I haven't done anything to the actual rule. It's still the exact same function. Next step is the big one, the biggest one. Step 2 is when you switch the x and y. At this point, I no longer have the same function because I interchanged them. This thing right here is the inverse. It just isn't in a function notation, but it is the inverse. Okay, so step 3 is to solve. How am I going to do that? Let's see. I'll multiply both sides by 7. Then I'll subtract 2 from both sides. Not that hard, is it? In fact, I'm ready with the y.
To the multiplying both sides by 7, and I was like, okay, whatever, I missed it.
Yeah, if you multiply both sides by 7, you'll fraction bust. I can show it right here. I don't like all those step numbers in my way. Here, I'll scoot it over. Okay, so step 4. We've already got it written like this. We just need to put F inverse because it was called F originally. If it was called G originally, we'd call it G inverse, and then we'd state the rule in terms of X. Put it in and tell us if we're right. The first one's a line and this one's a line. Does it want you to graph them when you're done? Sometimes it says graph them on the same grid.
Yeah, it was
7x minus 2, good. Did it want us to graph them?
Yeah.
Okay. I've already got a grid. I feel like I have to graph it now. This first one would have been nicer to look at it as 1/7, oops, 1/7 x plus 2/7. And with that being the case, I'd want to make big blocks. Okay, and then the original graph would have started at 2/7, so maybe about right there. And then you go up 1 to the right 7, so up 1 to about right here, to the right maybe about right there. Total sketch, so don't worry about this. The next graph, I'll graph this inverse in green, would be go down 2 and then go up 7 over 1. So 1, 2, 3, 4, 5, 6, 7 over 1. Connect the dots. Yeah, I know it's not perfect, but you can see how there's your y equals x line, and if you folded them, they would have matched. Want to try any more? A cube root one?
Yeah.
Okay, let's do it. Tell me what number.
2.
Is it called f of x or is it called something else? Okay, they're not very creative, but just keep in mind you could call this any letter you want. You could call it Bob of x. Don't get caught up on this is the name part, and then this is what dummy variable it's going to use in the rule. And go ahead and give me the rule. Cube root.
Yeah, x plus 2.
Cube root is the x plus 2 all inside.
Yes.
Okay, cube root x plus 2, and to be clear, it's all inside. So they could call it the g function, they could call it the f function, they could call it the Jameson function. That's just the name part, and then this is the dummy variable that's going to be used, where you plug in that number, and you get out some sort of output each time. I'm going to go back to the correct name, and then let's do it. Step 1, use Y notation. Step 2, the critical step. Yeah, switch them, interchange them, whatever you want to say. At this point, you have now changed your entire function and rule, and that is technically the inverse.
Things you can't really solve by rule.
Just because by doing that in the rule, you technically did it for every ordered pair that would have ever been created by the rule, so you've changed the rule. You've created a new graph, a new function. And since it was one-to-one, this one is a function. Step 3, solve that. So let's see, how would you solve that? We did those in section 10.6. Do you remember that?
Cube it.
Yes, cube it, good.
I want to say square, but it's not, yeah.
Yeah, cube it, and then it will undo itself right there, right, on this side.
Yeah.
Undoes itself. And now you've got x cubed equals y plus 2. You're trying to get y by itself, so yeah, exactly, Jessica, just subtract 2. So then you got x cubed minus 2 equals just y. I don't mind, like on the PowerPoint, you know how it reflected the equation? I don't like to reflect it. I actually like to leave it here, because then when I go to step 4, since the y is already hanging out off there to the side, I can just strap in my inverse notation right there in front. And that's my result. I'll write it as a separate line, but it's kind of not necessary. This is your result. I won't bother with the graphs on this, but you would just know that the graphs would reflect about the y equals x line. But look how nice that is. Then do y notation, switch the x and the y, or interchange them, whatever you want to say. And then do the solving technique, which this one would require us to cube both sides and then to subtract 2, and then just slap this on it. That's the result. Any questions on that? Okay, let me stop the video here.